Okay, so let me start. We were looking at codecs, so especially I was telling you about basic coding theory techniques, and we talked about classical error correction, what are the codes, and so on, generator matrix, parity check matrix, right? And then I also talked about array decoding and probability decoding, right? So now we also talked about syndrome decoding, and I gave you an example of Hamming code. Okay, we were looking at cyclic codes. As I mentioned to you, that most of the good codes are cyclic, and once you have a cyclic code structure, making circuits for encoding decoding is quite easy and easy to handle the stuff, right? And so, what are the cyclic codes? So, cyclic codes are codes which are linear, of course. Number one condition, they should be linear. That means they are a subspace of the whole vector space of dimension n. Second, any cyclic shift of a code word is again a code word. So if C0, C1, Cn minus 1 belongs to C, the shift also belongs to C. Okay. So, and if this belongs to C, that means its shift also belongs to C, and so on. Everything is a member of C. So this is something a very peculiar and important property. Okay. And now, if I want to capture this idea mathematically, we require the machinery of what is known as polynomials. So I'm mapping each code word C0, C1, Cn minus 1 to a polynomial C0 plus C1x plus C2x square, and so on up to Cn x raised to power n minus 1. I call it Cx. So when I multiply x times Cx, it gives us one cyclic shift, because now we are getting this polynomial. Now certainly the degree is there n minus 1, so this is more, so this should be 1. So then everything shifted. You can see that this becomes the constant term of the polynomial, so the first term. Okay, and so on. If you multiply again with x, so that means x squared times Cx, 2 cyclic shift. X cubed times Cx, 3 cyclic shift, and so on. Right? So like that we can do this cyclic shift. Now let us look at an example and see some interesting properties when we actually do this business. So I am looking at our whole space Z23. So you know that we have a vector 0, 0, 0. Right? The first vector in this Z23, three-dimensional space, there are 8 vectors altogether. So now this will map to 0 polynomial, because 0 plus 0 times x plus 0 times x square, like that we can compute. So which is essentially 0 polynomial. Then we go to say 1, 0, 0. 1, 0, 0 will be what? The first coefficient 1. So 1 plus 0 into x plus 0 into x square. So this is 1. Fine. What about 0, 1, 0? So the first coefficient is 0. So see what we are doing. So C0 plus C1x plus C2x square plus dot 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 Cn minus 1 x raised to power n minus 1. This is what we are doing, right? So 0, 1, 0 means x only, right? Because middle coefficient is there. Then we go to 0, 0, 1. This will give you what? First constant term is 0, middle term is 0. You are getting x square, right? Then we can look at, so these are all weight 1 vectors. Now if you look at weight 2 vectors, one vector will be 1, 1, 0. 1, 1, 0 will be what? 1 plus x. Then we have 0, 1, 1. This will correspond to x plus x square. Then we have 1, 0, 1. This will correspond to 1 plus x square. And then we have 1, 1, 1. This corresponds to 1 plus x square. Right? All the 8 vectors correspond to these polynomials, right? I've just mapped. Now I will show you the beauty. We have the whole space in terms of polynomials. Out of these polynomials, what I'm going to do, I will look at this polynomial, x square plus x plus 1. Are you familiar with this polynomial anyhow? Discrete math class mein shayad you may be remembering. We have constructed field with 4 number of elements using the polynomial x square plus x plus 1 because it has no root in the ground field, right? So if I take this polynomial and reduce everything with this polynomial, obviously x square plus x plus 1 is equal to 0 means x square is equal to x plus 1 because minus 1 is same thing as plus 1. Everything is modulo 2, right? So what you are going to get, first element will be 0, second element will be 1, third element will be x, fourth element will be 1 plus x because x square is equal to 1 plus x. X square I can get it off, right? Then this will remain anyway 1 plus x. What about here? X plus 1 plus x. So x will cancel it out, 2x, so you will get 1. Here, x square is 1 plus x, so essentially you are left with x, right? So you see that you will only get 4 elements, right? Well, when you reduce everything by this polynomial. So in fact, if I pick up this, so I will say that I have taken a polynomial f of x is equal to x square plus x plus 1, and I'm just writing in the terms of notation. Z2x is our this polynomial ring that we are getting actually. This thing we are getting, I call it as Z2x. Right? A polynomial with coefficient in Z2. Right? All the polynomials, right? So we are getting this Z2x. So Z2x modulo x square plus x plus 1 is what? Know that this is a field with 4 number of elements, if you remember from your previous class, right? Because ground field is having only, so the ground field, this polynomial x square plus x plus 1 is irreducible. It has no factors. I call a element alpha, and then I can write down GF4 as 0, 1, alpha, alpha square kind of thing. So basically, I can just show you the tables if you remember. We have 1 x plus 1 0. Right? We have 1 x plus 1 0. So what you are going to get? 0 x plus 1 x 1 x plus 1 0 1 x 1 0 x plus 1 1 x plus 1 0. When we are doing modulo x square plus x plus 1, we are getting only these 4 elements, right? So I can make an addition table. Similarly, I can make a multiplication table. I'm not writing this now, the multiplication table you remember, right? In terms of alpha we made, right? You can do everything with multiplication. Keeping in mind that x square is equal to x plus 1. So what we are doing, we are writing all the polynomials and reducing it modulo x square plus x plus 1. So now what you observe, when the polynomial was irreducible, this polynomial is irreducible, we are getting a field out of this, right? Everything is a field, right? Whatever we are getting. So now, so this is something interesting. Similarly, you can make multiplication table. I am not making it. But what if I choose a different polynomial? So just now you saw I have taken this polynomial and reduced everything modulo this, right? What if I take the other one? Say this is this polynomial x square plus 1. If you take x square plus 1 and reduce everything to x square plus 1, so first element will be 0, second element will be 1, third element will be x, fourth element will be 1. Because x square is equal to minus 1, same thing as plus 1. And this 1 plus x will be what? I mean, this will remain 1 plus x, no issue. Here x plus x square, so x square is 1, so this is 1 plus x, right? And here x square is 1 plus x, so 1 plus x plus 1. So essentially you will get x, right? And the last element you can find, because x square is, 1, so this is x actually. So you can again get certain elements when you reduce it to modulo. Now it turns out that when you make the table of addition and multiplication, it is not a field. And the reason is because x square plus 1 is a reducible polynomial over Z2, right? Because x equal to 1 is a root, you can clearly see. X equal to 1 is a root over Z2 for x square plus 1. So if the polynomial is irreducible, you are getting a field. When you make addition and multiplication table, everything is well organized. But if it is a reducible polynomial and you reduce it everything, you get a ring actually, you will not get a field because presence of 0 divisors. So I can make that table also for you and you can clearly see that. Now, if I take Z2x, all 8 polynomials, modulo x square plus 1. So now you can clearly see that with respect to addition, 1x, 1 plus x, 0, 1x. Actually, I will not make for addition because addition is straightforward. I mean, I'll show you the multiplication table, okay? I mean, that's something fine. You can do that. So we have multiplication table here. 1x, 1 plus x, 0, I'm avoiding because 0 multiply with everything is anyway 0. Multiplication table, 1x, 1 plus x. So 1 into 1 is 1, x, 1 plus x into 1 is x. This is x into x square, which is 1. And x into 1 plus x is 1 plus x, 1 plus x, 1 plus x. 1 plus x into 1 plus x is 1 plus x whole square, which is nothing but 1 plus x square. But x square is equal to 1, so the whole thing is 1 plus 1, which is 0. You just look at the multiplication table. In the previous example, when we took fx is equal to x square plus x plus 1, you look at the multiplication table, no such odd thing will happen here, right? So now this shows that 1 plus x is a kind of 0 divisor right here. So there is a problem. In the multiplication table, each column should have one, at least ek to 1 aana chahiye, right? So here it's 0. So that means 1 plus x is not a it's a 0 divisor, right? So every element does not have an inverse in this scenario. Whereas if you take fx is equal to x square plus x plus 1, every element has an inverse. But here it is not. Just by taking the polynomial, which polynomial you are taking, whole space, we are getting different things, right? So that means, in general, if I take our polynomial, so when we look at the whole space, z2 raised to power n, right? And write down all binary vectors in the form of polynomials. And if I take a polynomial f of x, which is irreducible over the ground field, we will get a field, right? But in general, it may not be a irreducible polynomial. So ultimately, you will get a ring known as polynomial ring. Okay. So z2x mod, this. So I can just write it down. So basically, if I take this z2x and I just take mod x cube minus 1. Our fx is this polynomial, suppose. Then what will happen? So why x cube minus 1? Because you see, when we are mapping, if you look at this, when we are mapping whole space into Z2X, right? So when we are doing this mapping and we want what we want in our cyclic property, that cyclic should be justified, right? So x raised to n should be 1, right? Because then only the term will come toward the first one, right? So that is giving us this condition. Here n is equal to 3, so x cube should be 1. Whenever we are doing these calculations, right? X cube should be 1. So that's why I am actually dividing the whole space with this polynomial x cube minus 1, because x cube is equal to 1, right? That means x cube minus 1. So that means I'm going to get, so normally this is known as R3 ring. Why it is ring? Because f of x is x cube minus 1, which is a reducible polynomial. X cube minus 1 is a reducible polynomial, right? If it is irreducible, then everything is fine. But here in general, it is not. So x cube minus 1. So when we are doing this cyclic code business, we are converting everything into the cyclic ones. Actually, we need to take care that everything should be x cube is equal to 1. So, or x raised to n is equal to 1. So whenever we are putting this condition, so we are taking the polynomial in Z2x modulo x raised to n minus 1. So this is our polynomial ring. We call it as Rn. Okay, Rn. Now we would like to see what happens to the cyclic code. I mean, what happens to the code? So code is nothing but normally in the whole space it was a subspace. So I looked at what happened to the whole space. Now I need to look at what happens to the subspace. You know, bunch of vectors which were closed with respect to linearity, linear space. Code is nothing but the linear space, right? I have taken care of the cyclic business by introducing this x cube minus 1 is equal to 0 means you take the whole space of, so in general, actually, I should say that I can write it down like this. So Z2x mod x raised to n minus 1. When we're looking at length n, this is a polynomial ring for any n. I'm just showing you an example for length n is equal to 3, right? So Z2x is the whole space, right? You just map whole space and then you reduce it to whole thing with some polynomial fx is equal to, okay, x raised to n minus 1. Now, if I look at, I go back here, if I look at a code C as 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1. This code is a cyclic code. It's a linear code, right? It's a linear code. It is also a cyclic code, right? Because everything is cyclic shift is closed. We have seen with respect to vectors. What happens to this code now when we do this mapping? Now, when we do this mapping, it turns out that this becomes, I denoted by I, or you can also call it C, no problem. C as, when you look at the polynomials, 0, 1 plus x, 1 plus x squared, x plus x squared. This becomes this set, right? Everything is converted into polynomial by that mapping. Now, what are the properties of this set now? This set as a, subset of polynomial ring R3. R3 is Z2x modulo x cube minus 1. And this set should have some relationship. People who are doing algebra course or those who are familiar with algebra, it turns out that this linear code becomes ideal of the whole ring. Like again, kind of subspace, you can think loosely. It's an ideal of the whole ring. So let me show you what does that mean. So basically, our code I is equal to 0, 1 plus x, 1 plus x square, x plus x square is an ideal of R3. Ideal of R3. So what is the property of ideal. Let me mention what is the property of ideal. So now I should give you a definition. If R is a ring, okay, a non-empty subset, I is non-empty. Non-empty subset of R is said to be ideal if, number one, A plus B and A minus B belongs to I, for every A comma B belongs to I. If I take two elements of the set I or C here, right? This is C or I, whatever you call. I take any two elements, add or subtract, it should be in the sub space. Second, for every, so R into A belongs to I for every R in R and A in I. Means it's closed with respect to left multiplication. You take an element A from the ideal, from this set I, multiply with an arbitrary element of the ring R3, you will get a member of I. Can you check this property, whether this holds? Suppose we take A is equal to 1 plus X. Suppose we take A is equal to 1 plus X. What happens now? If we take A is equal to 1 plus X, right? So R is element of ring. Here our ring is R3, having those 8 polynomials. So if you multiply with 0, suddenly it will be in I, first element. Take the second element, which is 1. 1 into this 1 plus X, then again will be in I. Take the next element, X. What happens if you multiply this thing with X? X plus X square, which is a member here, right? What is the next element? 0, 1, X is there. 1 plus X, right? If you multiply this whole thing by 1 plus X, this will be 1 plus X square, which is again in the set. What is the next element in the list? X square. If you multiply this thing with X square, this is X square plus X cube. But X cube is equal to 1. So this is 1 plus X square, which is again in the set. What is the next element? X plus X square. So if you multiply X plus X square, what comes out? You can multiply and simplify, right? Assuming X cube is equal to 1. You will see that again it is an element. So basically you take all the 8 elements of the polynomial ring R3 and multiply with this element, you are getting a member in the I itself. So this property is satisfied, right? And the first one is fairly easy, right? Addition or subtraction, which is true anyway, right? You can see that. So all these two properties are satisfied. So that's why this set I turns out to be an ideal in the ring R3. Okay. So that this is a very beautiful thing actually. We were dealing with vectors. Now we are dealing with powerful algebra. So the ring and the ideal. So I need to only worry about the ideal. So if I have to find a new cyclic code, I should worry about the ideal, right? Now this ideal has also one very important property. Each of these ideals. So just like that, in our whole subspace, we have basis vector, right, which can generate the whole space. Here, ideal can be generated by one element. There is a generator. So let me show you that. So I would say that if I take, so our R3 is X cube minus 1, and I is our 0, 1 plus X, 1 plus X square, X plus X square, right? One can see that I is generated by 1 plus X. Because, all the 4 elements you can obtain So when you multiply R times 1 plus X, R belongs to a member of R3, you will get I. Because you see, when you multiply all of them, you will only get 4 cases. When you multiply everything, so you just multiply one arbitrary element to an element of I, you will get some value, some polynomial. Take second value, you will get some polynomial. And when you do this, there are total 8 possibilities. You will see that ultimately it will lead to these 4 cases only. So essentially, there is a generator, I am saying that. This ideal is generated by 1 plus X is a generator. So 1 plus X can generate everything. So this is also known as principal ideal. Okay. So there is a generator. Okay. So basically, so we call it as a I is known as principal ideal if there exists an element A in I such that I is nothing but generated by G. So what do you mean by this? G times R times G such that R belongs to R. Right? So this is the overall machinery. So basically now you know that beautiful algebra is coming into picture to handle the cyclic codes, right? So let me give you some more properties about. So I hope now you got this idea that once we have the whole space can be converted into a polynomial ring modulo x raised to power n minus 1. Why we have this x raised to power n minus 1? Because we need to keep the track of cyclicity, right? So we need to introduce this condition that x raised to power n is equal to 1. And that means if I have to find a code, just look at any ideal of the ring Rn, and that will be a cyclic code of the cyclic code. That's a beautiful thing. It will be a cyclic code, right? So give me one question answer. If I have to find cyclic codes, what I should do? Of certain length, suppose n is 7. What we should do? So basically, let me build a little bit machinery so that you can think. If I have to find a cyclic code of certain length, what we should do? Actually, we only need to worry about factorizing the polynomial x raised to power n minus 1. And we are all set actually. Just factorize the polynomial x raised to power n minus 1 and take each factorization as a generator polynomial of the cyclic code. So let me show you what does that mean. So I'm not giving you any proof, but rather mentioning the fact. Okay. As a result, if C is a cyclic code in Rn, you know, V2x or x raised to power n minus 1. Result holds for non-binary case as well, but I'm just mentioning the binary case. First, there exists a unique monic polynomial Gx of smallest degree in C. Second, C is generated by this Gx. Third, Gx is a factor of this point minus 1. It's essentially, if C is a cyclic code in Rn, that means whenever we are looking at an ideal, now you can look at that example that I have given to you, that you can always find a monic polynomial, unique monic polynomial of smallest degree in C, right? In C. So in the previous example, there were four polynomials, right? So 1 plus x is such a smallest polynomial here. which acts as a generator. Okay, C is generated by 1 plus x, and in fact 1 plus x is a factor of x raised by n minus 1, which is also true, right? Because remember here plus 1 is same thing as minus 1, all those things I'm assuming, right? So basically it is a factor of x cube minus 1, right? So basically in our example it is factor of x cube minus 1, right? So these properties hold. So whenever C is an ideal in the ring Rn, you can find a smallest monic polynomial Gx which will generate everything, right? And this Gx is a factor of x raised by n minus 1, right, in general. Okay, so this is the key property. Of course, I am not giving you a proof, but so one question that you may ask is, suppose we are, so basically if I have to find a cyclic code, as you can see that all what I have to do is look at the factorization of x raised by n minus 1, take the one factor and take it as a, it's if, because obviously it will be, monic polynomial of the smallest degree and so on, right? So you can, using that polynomial, you can build the cyclic code, right? One question remains that once we know the ideal, right? Or we know the, so we know the factorization, that means we know the Gx, we can generate the ideal out of it, right? How to get the generator matrix? What, is there any way to go back from the polynomial business to the generator matrix? And that answer is yes. So I'll just mention again the result. Matrix is something like this. If Gx is G0 plus G1x plus dot 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 GR, X is for R, then C is generated by as a subspace by the following generator matrix: G0, G1, GR, 0, G0, G1, dot 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 GR, and 0, 0, 0, 0, G0, G1. This matrix from the generator matrix will do our job, because total length is n, so that's why there are all zeros, right? This generates, so from the polynomial, I can write down the generator matrix. Okay, and this will give you one question you may ask. This generator matrix is not in the standard form. Identity block is not there, right? The standard form of generator matrix is IK slash some A matrix, for some A matrix, right? That is not here, but there are certain modifications which you can do in the polynomial business. I leave it to you, because then it will be too many things to discuss. Okay, if you want, you can look at this by lectures of the previous coding theory class where we described more details. But I think this much is sufficient. So you know that from the Gx, how to construct G. Okay. Now, how to find all binary cyclic codes of length 3. I'm just giving you a small example, and then I think the rest I'll leave it to you so that you can actually find it. How to find all binary cyclic codes of length 3. So what I need to do, look at the polynomial x cube minus 1, right? Look at the polynomial x cube minus 1. So I know that x cube minus 1 can be factored like this. Right? Can be factored like this. So obviously, so these are the two independent factors, but overall, how many factorizations are possible for x cube minus 1? 4. How? 1 will be 1 into this, right? So 1 is also there, right? And another one will be you take whole thing as a product, right? So one thing will be x cube minus 1. So there are those two trivial boundary cases, 1 and x cube minus 1. And in between there are two factors, right? So total 4 possibilities. So I can write it down, each of these possibilities here. So generator polynomial, code in R3 and code in when generator polynomial is 1. So 1 into 1 plus x into 1 plus x square. 1 is also factor, right? If it is 1, this is all of R3. All 8 polynomials will be there. And this is all of C to 3. All 8 vectors corresponding. Trivial case, right? When polynomial is x plus 1, generator polynomial, we know that code is 0, 1 plus x square, and x plus x square. You just saw this is an ideal, right? And the corresponding code here is 0, 0, 0, 1, 1, 0, 0, 1, 1, and 1, 0, 1. Right? The next case, when we take x square plus x plus 1, this will give us 0, 1 plus x square. 0, 1 plus x square. And this is nothing but, in case of binary, 0, 0, 0, 1, 1, 1. Your friend, repetition code, right? The one which we started with. When we take x cube minus 1, which is, of course, essentially 0. So this gives you 0. This is 0, 0. So, or all possibilities we can list, right? So if I have to construct a cyclic code of certain length, just you need to focus on factorization of x to the power n minus 1. Now, how to find factorization is another beautiful theory behind it, right? Okay. But I think you can clearly see that, in fact, so you see that even this code is cyclic as well. The beautiful small code that we've used, repetition code, right? This is also cyclic code, right? I can list down few of other factorizations so that you know what kind of things are there. N factorization of x raised to power n minus 1 number of cyclic codes. So when n is equal to 1, 1 plus x is the factorization, right? Number of 2 trivial cyclic codes. When n is equal to 2, it is actually 1 plus x whole square. 3 cyclic codes. N is equal to 3, 1 plus x into 1 plus x square. You saw that. 4 cyclic codes you saw recently. N is equal to 4. This is 1 plus x raised to power 4. There are 5 codes. N is equal to 5. 1 plus x. 1 plus x square plus x cube plus x raised to power 4. Clearly, this will give you the repetition code with 5 things, right? There are 4. N is equal to 6. 1 plus x whole square. 1 plus x square whole square. There are 9 possibilities. N is equal to 7 is interesting case. 1 plus x square plus x cube. 1 plus x cube. And there are 8 total codes. N is equal to 8. 1 plus x whole raised to power 8. X equal to 9. 1 plus x. 1 plus x square. 1 plus x cube plus x raised to power 6. If I know this is 8. 10. 1 plus x whole square, 1 plus x square plus x cube plus x raised to power 4 whole square. This is just summary up to length 9. This case is really interesting. Can you tell me why this case is really interesting? N is equal to 7. Hamming code we constructed, right? Hamming code, length 7, right? 743. Yesterday I gave you an example. Actually, that is also a cyclic code. So, which one you should use. So I leave it as an exercise to you, find out which polynomial should I use to construct that code, Interesting exercise to see, which one will give you this cyclic code. So essentially, total 8 possibilities, but one of them will give you code. Okay. So I think if there is anything else left. Yeah, so now I should mention that some interesting cyclic codes are, and almost all of them are the Reed-Solomon code. So find what is GX. Reed-Solomon code is used in your QR code. QR code that you do, it uses Reed-Solomon code, right? And it is also used in a lot of storage. When you are discussing storage mechanism on your CD or hard disk, Reed-Solomon codes are used, or even DVDs. To a certain extent, Reed-Muller codes are also cyclic. Okay. Hamming code is a cyclic code, which I showed to you. By the way, the idea of Hamming code was generalized by Bose, Chaudhary, and Hockingham, and they are known as BCH code. So what are the GX in each case? You need to find it out. Right? What is the generator polynomial? So if I think now it's enough for you to look at the literature and see what are the generator polynomial. BCH codes are also known as mother of all codes. Okay. The idea is very simple actually. I just mentioned to you. You saw the generator matrix of the Hamming code, right? Those columns, 7 columns, right? So now they observed this, that, that Hamming observed that any 2 columns are multiples of each other, right? Of this Hamming code. Sorry, any 2 columns are linearly independent out of this Hamming code, right? So which can correct 3 errors. So they asked this question, what permutations of these columns I add to the next block as a next block, which can correct 2 errors. Okay, so distance will become 5. And just by doing the mere algebraic calculations, they were able to construct a beautiful code which can correct 2 errors with some modification in the parity check matrix. So basically, the parity check matrix approach will give an extension to construct. When you take 2 parity check matrices, so 1 parity check matrix and some function of it at the bottom will correct 2 errors. So 1 parity check matrix of Hamming code, another permutation will correct 3 errors. And then keep on extending like that. So as an engineer, BCH codes are very, very user friendly. If an engineer wants to correct certain number of errors, he chooses a BCH code of appropriate blocks, basically. Now, rather than doing this matrix business, you can do everything with polynomials because BCH codes are cyclic. So essentially, you have to come up with GX or bunch of polynomials to generate the cyclic BCH code, right? So that's a really beautiful machinery. It involves a lot of mathematics. I think I'm not going to do that here. But then it will be a coding theory course, right, class. So now we will be focusing from the next class, the actual codecs that are used in DNA storage, right? So this is enough for error correcting codes, a background, right? So if you have any questions, please do ask me. Any question? So Hamming codes have been generalized to BCH code. So it turns out that Reed-Solomon code were discovered in a different context. Turns out to be a BCH code only, a special kind of BCH code. So basically the construction of BCH code, one way is through matrices. That is how they were discovered. But later on, now people use polynomials. Okay, I have shown you some polynomial business with the cyclic code, right? So there are a couple of polynomials and there, some operations on them. Polynomials will generate the GX and the GX will give you everything, okay, as an ideal. So that's a very beautiful, interesting theory about BCH code. One thing I would like to mention that decoding of BCH code leads to a system of equations over finite field. And those kind of equations were discovered by, solution to those kind of equations was discovered by Ramanujan in 1918. Just purely doing mathematics for fun. He described a method how to solve these kind of equations in 1918. And in fact, Hardy used to say that whatever myself and Ramanujan has discovered will never be used anywhere in the, will have no application. And now it turns out that you see BCH code is the mother of all codes, and their decoding procedure requires similar kind of equations, right? So essentially, beautiful applications, right? So that is how things are connected. What you cannot sell today, you can sell tomorrow in mathematics, right? How to apply. That is something interesting, right? So I think that's all for today. So next class, we will be looking at now a couple of specific. Now I'll start with how the storage codecs were developed, what are their properties, and how, those kind of things we will be looking at more, okay, from the next class. Okay, thank you.